Friends, now this time I just want to type the things in front of you and want to give you a wonderful feeling that every programmer can experience. Let us consider the case of simple harmonic oscillator, and the first case we shall consider that is of damped type of motion. And in this damped type of motion, we can write equation. Let me call ODE1 as the differential equation, and the differential equation states as M into DIFF of x of t with respect to t. This I want second order derivative. So two times I have written t with a comma. That is equal to k, rather minus k into x of t. So here we have keyed in the differential equation, and now it can take a form the way we write the differential equation. Now immediately we can solve this differential equation, and that I shall call as SOLN1, that is solution 1. That solution 1 is equal to D solve ODE1, and you can just press enter key. So this will return you the solution of differential equation. Now normally under root k by m we call omega, and that omega is appearing here. You have two constants c1 and c2 appearing here, and if you desire to have a numerical value of differential equation, then you can just plug in some numerical values to m and k. I have worked out the randomly I have worked out the values for m and k, and let us try to utilize them. I shall call ODE2 as 100 into DIFF of x of t. Here this is second order derivative, and that is equal to minus 4900 times x of t. So this is a differential equation in numerical terms, and the solution SOLN2 is equal to D SLOVE ODE2. So this will give you very oftenly I commit this mistake. I have typed D solve equation wrongly, SOL, so it can solve that differential equation. And here omega is calculated. However, the constants are not calculated. Now we can again solve this differential equation for some boundary condition, and let us try doing that. SOLN3, this is third solution I am assigning as D SOLVE. I want that ODE2 should be used, and the boundary conditions are x of 0 is equal to 1, say at t equal to 0, the amplitude, the displacement is the up to the amplitude, and the amplitude I'm considering 1, and the velocity at that point, derivative of x at t equal to 0, that velocity is 0. At the extrema, that velocity is 0. So While writing this command, dsolve, I should use a curly bracket. I should open a curly bracket, then write the equation number ODE2, the boundary condition as, let us suppose that it begins from 1, and at that point velocity is 0. So if you enter this back, you will get a solution that x of t is cos of 7t. Now you can simply plot this, uh, plot. We want right hand side of solution 3, SOLN 3, and that is for t rolling from 0 to say 5. Then we can get a plot. So here you can see clearly that at t equal to 0, the pendulum is taken to an extreme position which we call amplitude, and at that point velocity is 0, and the moment it is released, it exhibits simple harmonic motion which reflects here. Now, in the second part, we shall consider a damped motion. So, uh, I want to write some text. So I'm giving number 2. This is damped SHM. Now I want again a math mode. So I'm clicking to math. Now I shall consider ODE. What was the last number that I have used? ODE2. Now I shall use ODE3 to write that differential equation, and it will be m. I am considering 100 into second order derivative of x of t with respect to t, that is equal to minus k, that was 4900, into x of t. So the damping factor is proportional to the velocity, and the damping factor being negative, I shall use minus some damping factor. Let's consider zero point 0.5, or zero point 0.5 will be less. Let's consider that. Let us consider that damping factor to be 10, into that being proportional to velocity. I should write first order derivative of the displacement with respect to time. So this makes a complete sensible differential equation, and it looks like this. Now we can solve this differential equation for the boundary condition. So solution 3 is DSOLVE. We are de-solving the equation, and this time we want ODE3 to be solved, and the boundary conditions, let us consider same. X of 0 is equal to 1, and that velocity is 0. So derivative of x of 0, this is equal to 0. So this will offer us some solution. Friends, again I missed writing the curly brackets here. So I should write curly bracket for the differential equation and boundary condition, and then should press enter so that I can get the solution of differential equation. This looks a little clumsy in the term that this is the amplitude which is disintegrating with time by that factor 1 by 20, which is determined by the damping parameters, and here we have 1 by 20 under root some number into t as omega, and let us try to plot this out. For plotting, we can use a command plot, and we are interested in plotting right hand side of SOLN3, and we want t to roll from 0 to 10. Let us see what happens. Yes, it is showing wonderful damping. Now I want to look at this up to 50 seconds, and this will return me how the damped motion of a harmonic oscillator disintegrates from amplitude 1 to some value. So here you can make a plot up to 100 seconds also and see how it diminishes off. Now we can play with this equation in a better sense, that if the mass involved, instead of 100 kg, the mass involved is 10. Sorry, I should change things here. So if it is 10, then we shall look at the solution and we shall look at the plot. So it disintegrates even faster. And if we increase this to 500 kg, let us look at the solution and how the plot goes down. Now I want to emphasize here on a factor that if you change the boundary condition for this equation uh, such that x of 0 is equal to 0.5, so the solution will go accordingly that way. And if this velocity is not 0 at this point, let us suppose that it is 0.3, then uh, how it behaves. So I just want to see both the plots at one time, then I can do that also. For that, let me make the parameters same. Let this be 100, and for that 100, we can see the solution like this. And now I want plot of solution 3 as well as solution 2. So there is some conflict, it appears. Solution 3 is this. Let me call this as solution 4, and then here I have to use solution 4. And now I want to see the two plots at a time, solution 3 and solution 4. Plot SOLN3 as well as SOLN4, and this is to be plot for t rolling from 0 to 60. Friends, again I have committed a mistake of choosing a wrong bracket. Here to plot many functions at a time, you should use a square bracket. So uh, let us replace that curly bracket by a square bracket, and let us once again try how the solution goes. Oops, I'm committing mistake after mistake. Here I should write right hand side of solution 3. See, one has to be very cautious. Now I'm making only one plot at a time. Solution 3 uh, and solution 4. Then comma, right hand side of solution 4. So it has not picked up that solution 3 and 4 because some assignment has gone wrong earlier. So uh, in undamped, we are having SOLN 3, fine. And then here we have SOLN 4. So to be very particular, we should restart the running of the worksheet, and by virtue of that, here solution 3 is now properly assigned, and now for damped oscillator solution 4 is assigned, and solution 3 and 4, yes, correct. The first plot of undamped solution 3 is appearing on the screen, and solution 4, it is damped, it is disintegrating. To make a clear resolution of the figure, you can stretch the figure and really look at what is happening. So it is very amazing thing that Maple has plotted damped solution and undamped solution. Thank you so much. Welcome back, friends. Now we shall use Maple to study growth and decay of current in LCR circuit. After this discussion, I believe the smaller combinations LRC, RRC, this should not cause any problem. And in fact, this is the toughest combination of circuit for B.Sc first year students. And this is the longest differential equation to be treated in the B.Sc first year. To make it very clear, I would first like to discuss the entire treatment which we do in the classroom manually, and then we shall do things very quickly using Maple. The basic circuit goes as we have series combination of resistor, inductor and a capacitor. It is excited by a DC source. You can imagine a switch in between, and the moment battery is connected, how current in the circuit rises, that we are studying. Now let us suppose that V is the potential applied by the battery, and as the combination of components is in series, it will be essentially, V will be essentially equal to sum of drop across R plus drop across L and drop across C. Now at the first outset, we shall write Kirchhoff's voltage law, that total battery potential is equal to the drop across capacitor, that is Q by C, and drop across resistor R into I, and L into di by dt will be the drop across inductor. Here current we are writing rate of flow of charge, so that becomes a second, this is a second order differential equation. Now we shall replace E by Q0 by C, that is a steady state value, and we shall rearrange this equation and substitute R by L equal to twice B and K square equal to 1 upon LC. So this equation, this very equation, we shall have that substitution, and that leads to this equation. So second order time derivative of transient charge plus twice b times first order derivative of transient charge plus k square into q minus q0. Q0 is something that is determined by the battery potential. By doing that substitution, and one more substitution we are having, we are putting a quantity x of t equal to q of t minus q0. Q0 being a numerical value, the time derivatives will be simply replaced by x of t, and here we'll get rid of this q of t minus q0, and this differential equation becomes a simple differential equation which is of second order. It has a standard solution, x of t equal to e to the power lambda, and lambda is a parameter which depends upon b, k, and obviously Bk depends upon RCL of the circuit. Now, as this is a solution, it should necessarily satisfy the basic equation. So we shall substitute x of t equal to e to the power lambda. If you find second derivative, it will be lambda square times this exponential function. So when you perform that, so we get this equation. So here we are in the bracket, we are having a quadratic equation in terms of lambda multiplied by the solution e to the power lambda t. Product of two things is vanishing. It does mean that either of them is zero. And the moment you consider the solution is zero, then the story is totally meaningless. Therefore, it is quite obvious that the first part, which is quadratic in lambda, that vanishes. So we can use roots of equation, quadratic equation minus b plus minus under root b square minus 4ac upon twice a, and this appears as lambda equal to minus b plus minus under root b square minus k square. Here we shall write this as minus b plus minus alpha, where alpha is that under root. Now that we have two roots, the lambda 1 and lambda 2, lambda 1 for plus minus b plus alpha and lambda 2 minus b minus alpha. So for that we can write the solution of the equation as linear combination of the two solutions where we are using lambda 1 and lambda 2. So x of t is equal to e to the power minus bt inside bracket a into e to the power alpha t plus b into e to the power minus alpha t. Now we can revert back the substitution. X of t is equal to q of t minus q0, and we can again find the first order derivative. Then we can employ the boundary condition at t equal to 0. The charge in the circuit q of 0 is equal to 0, and at that instant of time when charge itself is 0, the current, that is d dt of q of t, is 0. So if we enforce the first boundary condition, we obtained this equation, and by enforcing second boundary condition we get another equation. Now here we are interested in finding what is A and what is B. So we have two equations to be solved for two constants. Now I just don't get into fine details. You can very well do the substitutions and some mathematical processing, and you can obtain A is equal to minus q0 by 2 into 1 plus b upon alpha, and similarly B is equal to minus q0 by 2 into 1 minus b upon alpha. Now plugging in every damn thing, we get the solution in this fashion, where we have q equal to q0 minus q0 e to the power minus bt inside bracket e to the power alpha t plus e to the power minus alpha t by 2 plus b upon alpha inside bracket e to the power alpha t minus e to the power minus alpha t by 2, where alpha is b square minus k square. Now there are three possible combinations, that alpha can be real, alpha can be imaginary, and alpha 0. Let us tackle them one by one. If alpha is 0, then alpha is real, in that case the first bracket is hyperbolic cosine of alpha t, and second bracket is hyperbolic sine of alpha t, and this gives solution like this. And the complete solution in terms of LCR, we are getting this one properly arranged. In case alpha is 0, then e to the power 0 plus e to the power 1 upon e to the power 0. So that makes 1 plus 1, 2 divided by 2, and here this term vanishes. So in all, we get the complete solution as q equal to q0 into 1 minus e to the power minus rt upon twice l. The third case is a little clumsy in the sense that alpha is imaginary, so alpha can be written like this: I times k square minus b square, where you can call b square is equal to k square minus b square. Sorry, beta is equal to under root of k square minus b square. So here we can have cosine and sine function, unlike in the first case hyperbolic functions, and some small rearrangement makes it like this. So q equal to q0 into 1 minus e to the power minus bt upon sine theta into sine of beta t plus theta. Now e to the power minus b upon sine theta, this is kind of amplitude associated with sine function, and uh, and this quantity can be fairly looked as k into k upon beta into e to the power bt. So as time grows, this becomes vanishingly small. So the amplitude function, which is associated with this sine of beta t plus theta, it is diminishing with time, and the frequency of oscillation omega is simply beta equal to under root of k square minus b square. So here you can look for period and all other things. Now we just want to tackle this equation. Now let us try hands-on on this equation. Uh, Let me define this equation by name ODE, say 1, and this is L inductor into di by dt. So if we are talking in terms of q of t, then it is second order derivative L into di by dt plus R into I. R is a resistance into di double f of q of t plus q by c. So q of t divided by capacitance c. This is equal to the total battery potential that we have applied. So this is the differential equation which we intend to solve. Now, if rampantly we want to solve this differential equation encompassing all procedure that we have done earlier, so uh, the solution will be SOLN1. Rather, let's follow the same thing. SOLN1 is DSOL ODE1, and let us see the output. So the DSOL command has solved this differential equation. Now we shall solve this differential equation for the boundary conditions, and BCS now we are going to call boundary conditions, that is Q of 0 is equal to 0 is one boundary condition, and derivative of Q of 0 is also 0. So current in the circuit is 0 at t equal to 0, and charge in the circuit is also 0 at t equal to 0. Now let us solve this differential equation for the given boundary condition, and let us call that solution as SOLN 1 because first part we are keeping it reserved for growth in the circuit, growth of charge in the circuit. So this is equal to uh, desolve that equation, and in the curly bracket we have to state that equation is ODE1, and that is for boundary condition BCS. So here we have got the solution. Now to see the solution in proper way, I'm reducing the font size. So this is what that equation is. Now I want to plot this equation and fairly see in the region of interest how the quantities vary. Now friends, we are going to do the most wonderful thing in Maple during this solution. Now I am picking up the equation in the clip. I've done a right click, copy, and now here we shall generate a plot command and later on explore that. So I am going into tools, assistant, and plot builder. So here you can plug in number of equations at a time. For example, we are having only one equation, and here we can add the equation, and this quantity is a y quantity. So we are having this quantity here, except. So here we have C, E, L, R, and T. So T is our real variable. However, the other things are constant things. Now expression we have keyed in, and that is okay. Now here I am selecting interactive plot with 4 parameters. On x-axis I want time, and time can be real only, so it's rolling from 0 to some value. Later on we'll play with this value. Now potential of the battery, uh, we can connect a 1.5 volt cell. So I'm making it 0 to 3 arbitrarily, it will select it to 1.5 volts. And here we are having slidable parameters as L, R, C. Inductor we shall roll from 0 to 0.1. Then R 0 to 0.5, and C 0 to zero point 0.1 microfarad. So 0.1, 2, 3, 4, 5, 6, and then 1. Now we shall preview what happens to our equation, and that is fairly okay. We can change the x parameter. Instead of 10, we can have it just 5, and we shall ask for the command, and a command will be generated. Now this command I am taking it into clipboard, copy, and again I shall paste it here and place a end of the statement as semicolon, and it will generate the plot that we are seeking. Now if you decrease the value of R, then the oscillations will last for some longer time. So basically this is a very high frequency oscillation, those are taking place here, and that frequency is determined by the capacitance. So as we are trying to make it smaller and smaller, we can resolve that frequency. Now to have a fairly good look at this, the x, x value that we try to acquire, that we should select in proper range. That is the only issue I believe. Now see, looking at the equation and the plot, it is quite obvious that things are happening even in time less than 1 second for the values we have selected. What I have done, I have selected variation of t time from 0 to 0.01 seconds. Now for this situation, we shall just preview our graph. So it looks like this, and the frequency is still quite high. And let us try to consider time even smaller than this. So e to the power minus 3 I shall try, and then preview. So here, as we change the values, now see what we have done. We have selected value of t fairly small, and we want to return the command again. So this new command I am trying to copy in the clipboard, and now I want to execute. For execution, I want to paste it here and place a semicolon after that to make the end of statement. Now here, that we can change the value of R, we can increase value of R, we can decrease value of capacitor, and we can see how the things roll around. So here growth in the circuit goes from this, it is fluctuating, and then it settles to this value. So still small L we shall try, and we shall vary the value of C by changing value of C. We can see how the things are rolling, and if we decrease value of R, then it will oscillate for longer time, and if we increase value of R, then the oscillations will stop. So this is as far as the growth in the circuit is concerned. Now we shall try decay in the circuit. Now for decay in the circuit, we need a small change to be carried out in the basic equation, and that basic equation, we don't have battery in the circuit, so E is to be replaced by 0. That is the only change. Now let us try this equation as ODE2, and for ODE2 we shall make only this change, that E is replaced by 0, and this differential equation is equation number 2. So this is how we enter the equation. Now the boundary condition is the second issue, that we have written BCS, that BCS are different. We are breaking the circuit, and that is the time t equal to 0. So here BCS, I shall call this as BCS2, and at t equal to 0 we switch the circuit off, and that time let us consider that we have some numerical value of charge which is non-zero, and the derivative of that, when rate of flow of charge at t equal to 0, this also we shall consider some value unity. And now we want to look at the solution SOLN2. This is dsol, your curly bracket in which ODE2 for BCS2. So here we can get that solution quickly. This is the solution, and now we can plot this solution. Let us grab it into clipboard. So this is copied into clipboard, and now we shall key in for assistant plot builder. We can press a expression, add expression. This is the value of y quantity, and these are the parameters. Now this time E is not appearing in the circuit, but definitely the decay in the circuit will depend on the initial value. We want interactive parameter, 3 interactive parameter. On x-axis we want real time, which can roll from 0 to say 1, and L, we shall try better values, 0.001 to 0.01. R we can select from 0.01 to 1, and C we shall select 0.0001 to this should be a smaller value, and the another one should be higher value, 0.123, and then 1. Let's try with this. So here you can look at the x value, and the frequency is obviously high. You can get rid of this by just plotting a graph up to 0.2 seconds only. So for this, x is 0.2 seconds, and we can preview now. So here you can look at the graph, and L you can change, and you can see what is happening when you change L. Then you can similarly play with the parameters, and here the background calculations are quite heavy, so your cursor is indicating it is busy. So we shall generate the equation. So we are done with the selection of parameters, and is yet not responding. So it is always better to save before going into some plots like this. So here you can very well see that the transient charge in the circuit is oscillating through the short-circuited circuit having no battery, and the capacitor was initially charged, and every time the current flows through R and C, and every time when it flows through R, it is losing some charge, some ohmic loss is there, and because of that, the amplitude of oscillation is monotonically decreasing, and this is how the things work. Thank you so much. This was the most complicated plot that we have seen as reference to the second order differential equations.